Welcome to Scale Up University. Welcome to Probability for Machine Learning course. So this is the lecture number 4 of module 1, and in this lecture we will be discussing two schools of probability thinking. So see, until now we saw how to measure uncertainty. That is, we saw probability quantifies uncertainty, and we also saw probability theory. It provides systematic rules for reasoning. Now, interestingly, like whatever probabilities we are calculating, like we are quantifying the uncertainty using probabilities. Now, those numbers, that probability, that number, there are two interpretation for that. So, what does a probability number actually mean? So, two interpretations are there for that, and hence we have two schools of probability thinking. Like we have frequentist and Bayesian. So, that is what we will discuss in this lecture. So if we look at the topics we will cover, so first we will see why two school exist. Then we will see frequentist probability. Then we will see Bayesian probability. And then we will be comparing these two schools. And finally, we will be concluding this lecture with why does machine learning uses both? Because in machine learning, we will make use of both. We will be using frequentist probability also and Bayesian probability also. So that all we will discuss in detail in this lecture. Why machine learning make use of both probabilities. So we will cover all the topics one by one in this lecture. So this is the lecture number 4 of module 1. So module 1 is what is probability, and this is the lecture number 4, that is two schools of probability thinking. And in this, like the first topic of this lecture is why two schools exist. So we have different interpretations of probability. So if we talk about that, so we have frequentist probability. So here we calculate probability based on repeated experiments. So probability comes from repeated experiments. Then we have Bayesian probability. So here the probability represents belief under uncertainty. So here we calculate probability based on belief under uncertainty. So probability represents belief under uncertainty in the Bayesian probability. So we saw different interpretations of probability. So probability can either come from repeated experiments, then it will be frequentist probability, or probability may represent belief under uncertainty. And if the probability is representing belief under uncertainty, then it will be a Bayesian probability. So here it's all about interpretation. Now one very interesting thing we will discuss, like both schools use the same mathematics and the same probability rules. So the idea is that in both of the probabilities, like either you take frequentist or Bayesian, when you will calculate the individual probability, you will use the same formula, like favorable event or favorable outcome upon total number of outcomes. So number of favorable outcomes upon total number of outcomes. So this is the basic formula of probability, and interestingly, in both the schools, we will be using the same formula. So both schools will use the same mathematics, the same probability rules, but the result we will get, it will have a different meaning when you will be interpreting it with the frequentist probability school. Then that number will have a different meaning. It will represent, it will have a more of like a statistical significance, like out of n number of experiments or out of n number of outcomes, how many times that outcome I got, something of that sort. But with a Bayesian school of thought, the same number you got will have a completely different meaning, because that number will represent belief under uncertainty. So here it's all about meaning and not mechanics, because mechanics is more of same, but the meaning, the interpretation is different. So it's about meaning, not mechanics. Let us look at one very interesting example to make it more clear. Let us suppose we have a classifier and it is taking an email and it is calculating the probability of that mail to be spam as 0.7. Now this same number will have different interpretations, and now let us try to decode that, and it will give you a very good clarity. So from the frequentist school of thought, if we look at this number, what it is telling? It is telling that in the long run, 70% of similar emails are spam. Because in frequentist, like this number 0.7, what it means is that in the long run, 70% of similar emails will be spam. But from the Bayesian school of thought, Bayesian school of thought, what it means, what this number means is, given current evidence, the belief of email being spam is 70%. So see, the same number 0.7, the same probability, it has totally different meaning. Because in the frequentist, the meaning is in the long run, 70% of the similar emails are spam. But Bayesian is talking about, like, if you give a email, so given the current evidence, the belief of email being spam is 70%. So same numbers, different meanings. So now it's very clear to us that why two schools exist when dealing with probabilities. Okay, now we'll look at the next topic of this lecture, that is frequentist probability. So frequentist probability is long run relative frequency. So frequentist probability answers questions like, if we repeat this experiment many times, how often will this outcome occur? So basically, if we want to calculate probability of occurrence of an outcome, so in frequentist probability, what we will do is, we will repeat an experiment multiple times and we will calculate how many times that outcome is occurring. So that is frequentist probability. Like, let us suppose if I toss a coin 10 times. So what is the probability of getting a head when I toss the coin 10 times? So we can say that, or we can see that basically, if we talk about key characteristics of frequentist probability, so it is based on repeated trials. It requires large samples. The interpretation is totally objective interpretation. No subjective belief is allowed. So basically, frequentist probability, it is based on repeated trials. As we saw, we have to perform experiment n number of times, then favorable outcomes we can calculate. It requires large samples. The interpretation is totally objective. There is no scope of updating the beliefs based on an evidence, like no subjective beliefs is allowed. It's totally objective interpretation. If we talk about the examples, coin tosses. So in this experiment of tossing of coins, the probability involved will be frequentist. Dice rolls and repeated measurements of something. So that's the frequentist probability. Examples. If we talk about the strengths, key strengths, so we saw that it is like objective interpretation. So it is deeply grounded in data. So that's a key strength. It is clear and objective. It works well with large data sets. If we talk about the limitations of frequentist probability, so one of the main limitation is that it needs repetition. It is highly objective, so it cannot express belief for rare events. one-off situations, because no subjective belief is allowed in frequentist probability. So it cannot express belief, and also it cannot make use of prior knowledge, because there is no concept, or there is no scope of prior knowledge and updating it using evidence. All that cannot be done in frequentist probability. So frequentist probability cannot make use of prior knowledge. We can discuss one real world example, that is A/B testing. So in A/B testing, let us suppose we ran an ad 10,000 times, like variant A was shown 10,000 times, but it got clicked only 520 times. Similarly, we have a variant B of an advertisement. It was also shown 10,000 times and it was clicked 480 times. So here definitely you will be calculating the frequentist probabilities. So probability of getting a click for A is 520 by 10,000, that is around 0.052, and probability for getting a click for variant B will be 0.048. So based on the frequentist probability, we will be choosing variant A, because probability of getting a click for A is more. So this is how frequentist probability works. So this one real example we saw, A/B testing, and this is giving you an idea how frequentist probability is used in machine learning or in real world. So most like classical machine learning evaluation metrics are frequentist in nature, like model evaluation metrics we use in machine learning, they they make use of frequentist probability. So they are mostly frequentist in nature. Okay, now we'll look at the next topic of this lecture, that is the Bayesian probability. So Bayesian probability is degree of belief. It talks about, given what I currently know, how strongly should I believe this? So Bayesian probability is all about belief, degree of belief. So based on the prior knowledge, what should be the belief and how we can update the belief based on the evidence. So all that is dealt by Bayesian probability. So if we talk about the key characteristics, so Bayesian probabilities, it involved prior knowledge. It involves prior knowledge, and what it is, what you believe before data or before training, that is a prior knowledge. Then we also have evidence. Evidence is the new observations. And then we have updating the belief, updating beliefs as data arrives. Now here one very interesting thing you will see, probability exists even without repetition. So in this Bayesian probability, there is no need for repetition. Even without repetition, probability exists, because let us suppose I have a single data point. Now, based on the arrival of new data points, I can keep on updating the probabilities. I can keep on updating the beliefs, because here probability is representing the degree of belief. So Bayesian probability, it works well with limited data. So here we don't need huge data. Even with limited data, it will work well. Bayesian probability. It works well with one-off events, and it works well with rare scenarios. If I talk about the strengths of Bayesian probability, it is flexible, it is intuitive, it mirrors human reasoning. See why it's flexible? Because the probabilities gets updated on arrival of new evidences, on arrival of new observations. It's very flexible, it's intuitive, because here beliefs are taken into consideration, and it mirrors human reasoning, because human reasoning is based on beliefs. We also keep on updating our beliefs based on the events, based on whatever we see, based on our experiences. We keep on updating beliefs. Like a small child, he is totally unaware about fire, but once he encounters fire, a belief is programmed, and all his actions will consider those beliefs. And definitely, this probability naturally handles uncertainty. Now, let us look at one real world example to understand Bayesian probability more clearly. So, let us take an example of medical diagnosis. So, suppose there is a disease, its prevalence is 1% of population. So, this is the prior knowledge I have. I have a disease and its prevalence is just 1% of population. Now, let us suppose we conducted a test and the test result is positive. If the test result is positive, so this is the evidence. So how Bayesian probability works is that, so we start with the prior knowledge, we update the prior knowledge based on the evidence. So we had a prior knowledge, prior belief, we got an evidence, and based on that we updated and we got a posterior belief. So here the prior knowledge or prior belief is that the probability of that disease is 1% of population. Now we got an evidence that a positive test result. Now definitely the posterior belief will be that because of this evidence we will update our knowledge and we will say that more than 1% population might have. And similarly, if we keep on getting more and more positive test results, we will keep on updating our belief. So this is how it works, Bayesian probability. So three important components of it: prior knowledge, evidence, and posterior belief, which is basically updating the prior knowledge based on the evidence, and we get a posterior belief. So here probability is changing step by step. So we can say that Bayesian thinking is belief updating under uncertainty. So basically what we are doing is that we are updating the belief under uncertainty. Because why uncertainty? Because see, whatever prior knowledge we have, that might not be correct. And based on whatever evidences we are getting, step by step, we are updating the belief. So we are updating the belief under uncertainty. And that is what is Bayesian thinking is all about. And that is what is Bayesian probability is all about. And it is very important. It is very, very important, especially in generative AI. It plays a very important role. Bayesian probability. Okay, now we will look at the next topic of this lecture, wherein we will be comparing the two schools, comparison of the two schools. So let me first take frequentist, then let us also take Bayesian. If we talk about the meaning, so frequentist is all about frequencies. It is measuring the frequency. And Bayesian is the core philosophy, belief. The core principle is belief. If I talk about data requirement, so frequentist school, it needs large samples. And Bayesian, it can work with small data. If I consider the aspect prior knowledge, so in frequentist, prior knowledge is not used. There is no concept of prior knowledge, but Bayesian makes use of it. Explicitly it use. If I talk about machine learning relevance, so it is basically classical statistics, wherein we saw that in like model evaluation metrics, we make heavy use of this. So it is basically classical statistics. So frequentist probability is used in classical statistics in machine learning, and Bayesian is used in modern ML and AI, like in modern machine learning and in modern artificial intelligence, especially the generative AI. Bayesian probability is used. So we can say that Bayesian methods shine when data is scarce. So here we compared the two schools of probability thinking, frequentist and Bayesian. Now we will discuss the last topic of this lecture, that is why does machine learning use both. So first let us discuss frequentist roots in ML. So like maximum likelihood estimation, it is based on frequentist probability, loss functions, cross validation, hypothesis testing. So these all like are make use of frequentist probability. And definitely all these methods, like they need large data sets and they need repeated sampling. So repeated sampling plus large data sets. If we talk about Bayesian thinking in modern ML, so it is used in model uncertainty estimation. It is used in probabilistic predictions. It is used in Bayesian optimization, and it is used in Bayesian neural networks. And with Bayesian thinking, we can answer questions like how confident is the model? What does it not know? Now let us look into one very interesting application of Bayesian thinking to make things more clear. Like we saw, Bayesian thinking, it enables model uncertainty estimation. Now what it is, let us look at it to get more clear insights. So we call it uncertainty aware predictions. Now what is the meaning of this uncertainty aware predictions? Let us try to understand. So let us suppose I have two models, model A, model 1 and model 2, like two different machine learning models I have. Let us suppose both of them predicted A, class A as the output, but one did it with a confidence of 0.99 and the another model did it with a confidence of 0.55. Now with the Bayesian thinking, like with the use of Bayesian probabilities, we can calculate this confidence. See, if you don't use Bayesian, then you cannot calculate this confidence. So like let us suppose you made two models, it predicted an output, like both the models predicted the output to be class A. Now the answer is correct, the output is correct, and both of them predicted it correctly. But with the Bayesian probability, we are also able to estimate the confidence. So we can say that model 1 predicted class A with a confidence of 99%, and model 2 predicted the output to be class A with a confidence of 55%. Now this confidence of 99% is very much dangerous. It is like overconfident. So here model 1 is giving us a suspicious answer, because see, model 1 definitely it predicted the correct output, but this confidence of 99% is highly suspicious. Something is wrong with model 1. We can say something fishy is there with the model 1, and we are able to decode this with the power of Bayesian probabilities, because with the use of Bayesian probabilities we can calculate the confidence, and that confidence will help us in. So now what we can do, wherever some confusion is there, because whenever some like 99% confidence is highly suspicious, what we can do, we can bring in human in the loop. So if you are automating something, so whenever such scenarios arises, whenever you get a output with a very high confidence, then that is a suspicious output. You can bring in human in the loop. So that's the beauty of Bayesian. So what we can say, like we can conclude is frequentist methods train models. Like with the help of frequentist methods, we can train model. Like we can do the maximum likelihood estimation, loss functions, we can estimate cross validations, hypothesis. So frequentist methods play a role in training the model, and Bayesian thinking, Bayesian methods, it help to trust them, because we saw with Bayesian we can also determine the confidence, and because of that whatever output I am getting, can I trust that? So Bayesian methods helps to trust those models. So this is a very important point we discussed. So now it's very clear to us that frequentist probability is more of like classical statistics based on the large data set, based on the repeated sampling. We do some sort of estimations, some sort of probability calculations. So it plays a role. It helps in training the model in machine learning. But when it comes to determining, or when it comes to trusting the model, whether we should trust the model or not, then we have to make use of Bayesian methods, because with the help of Bayesian methods, we can like determine whether we should trust the model or not. So now I think the picture is very clear, the difference between frequentist probabilities and Bayesian probabilities, and how and why machine learning makes use of both. So students, finally we completed this lecture. So in this lecture we saw two schools of probability thinking. We saw it in some good detail. I hope you got a very good understanding of frequentist probability, Bayesian probability, the difference between them, and how they are used in machine learning. Like a brief idea you got. And in this course, we will be discussing several lectures. You will get a very good, deep insights. So now we are building the foundations. In the initial lectures, we are building the foundations, and then we will go deep and we will explore some in-depth concepts. We will do some in-depth analysis. So I hope you liked this lecture. You got a very good understanding of the concepts. So do subscribe to our YouTube channel for more such interesting lectures and courses. And do share it in your circle. You can share it with your friends so that they can also get some good insights. So thanks for watching. Thanks for your time.